This reentrant flow is illustrated more clearly in the cavity trailing our supercavitating hydrofoil. Reentrant flow is characteristic of such cavity flows. The momentum flux in the reentrant jet is equal to the pressure drag of the body. The jet kinetic energy is dissipated. Another type of cavity flow occurs when a missile enters water at high speed. In this sequence, a steel ball is shot into a tank of water. Here, the camera is turned so that the water surface appears to be vertical and the missile to travel horizontally. The cavity follows the missile into the water and eventually closes off, producing reentrant jets which are seen here in slow motion. Initially, the gas within the cavity attached to the missile is air rather than vapor. Progressively, the air is left behind, and if the motion persists long enough, the cavity content will be vapor primarily. Still another example of cavitation occurs in the type of bubble chamber used for studies of high-energy nuclear particles. In this photograph, a positron-electron pair has produced a track of bubbles in liquid hydrogen, which is at a pressure below the boiling point and is therefore unstable. We have seen that cavitation can take several forms: small transient bubbles, large, more or less steady cavities, non-stationary cavities, and often a mixture of these types. Let's turn now to an examination of some of the effects associated with cavitation and cavitating flows. What happens to a machine when it begins to cavitate, and how does performance vary with increasing extent of cavitation? Since hydrofoil sections make up so many different types of machines, pumps, turbines, propellers, propeller shaft struts, mixers, we can illustrate what happens to all such machines by studying the forces on the hydrofoil section itself. We have suspended the first hydrofoil model from force gauges, which show us lift and drag on these scales. The flow speed is constant, and the gauges register the corresponding lift and drag. The ambient pressure is set at a level well above that at which cavitation can occur. We are going to induce cavitation by decreasing the ambient pressure in the test section, keeping the speed constant. At first, there is no appreciable change in either force. As cavitation develops, lift decreases and drag rises. You can see from the force balances that the flow is quite unsteady. When we lower the pressure further and allow cavitation to spread, the lift decreases further and the drag continues to rise. We can get an idea of what has happened by examining the pressure distribution on a hydrofoil section. This curve represents the pressure on the upper surface, and this one, the pressure on the lower surface, before cavitation begins. The lift is proportional to the difference in the areas under the two curves. As the ambient pressure decreases by a certain amount, the pressures on the upper and lower surface decrease by exactly the same amount, at least until the upper surface begins to cavitate. At this point, the upper surface pressure can no longer decrease below the cavity pressure, which is near the vapor pressure. Since the pressure on the lower surface does decrease, the lift drops. Actually, as cavitation develops, the shape of the pressure distribution changes somewhat. The resultant pressure distribution is such as to cause an increase in drag. Thus, hydrofoils, and for the same reasons, many hydraulic machines which are designed for efficient subcavitating operation lose efficiency when cavitating. Where cavitation is unavoidable, and conditions are such that supercavitating flow can be assured, it is possible to use supercavitating hydrofoil profiles specifically designed to achieve high lift-drag ratios. Another important effect is the noise that collapsing cavitation bubbles produce. A partial vacuum has been pulled in this space above the water column. As I accelerate the tube downwards, the inertial forces produce a pressure gradient in which the pressure decreases as you go down from the free surface. At some level, the pressure is low enough for the liquid to cavitate. The noise is a result of shock waves generated upon bubble collapse. The pressures associated with collapse are high enough to cause failure of metals. Here is cavitation damage on the runner of a large hydraulic turbine which operated under cavitating conditions for an extended period of time. This propeller operated under cavitating conditions for only a few days. Similar damage can be produced on pump parts, such as this impeller of a pump for high-temperature liquid sodium, and in the low-pressure regions of hydraulic structures, such as this large power dam spillway tunnel. There has even been speculation that brain damage can be produced by the collapse of bubbles in the cranial fluid when the skull is accelerated under the action of a sharp blow. To show you how quickly cavitation can cause damage, we will expose the surface of this aluminum button to a cavitating cloud. The cavitation will be produced in an alternating pressure field created by oscillating the specimen itself. The specimen is driven by this magnetostriction oscillator. We are looking directly upward at the face of the specimen. The total amplitude of vertical oscillation is only 0.02 of an inch, but the pressure is changed from below vapor pressure, as the button is accelerating upward, to a high pressure, as it is accelerating downward, at the rate of 14,000 cycles per second. After 1 minute, the highly polished surface has been eroded, and significant weight loss has already occurred. Here is a side view of this experiment. The high collapse pressures and the mixing caused by ultrasonic cavitation is put to good use in industry. For example, for accelerating chemical reactions, industrial cleaning, and homogenization of milk. Let's now look more closely at the motions of the small transient bubbles which cause so much trouble. These bubbles have a life history measured in milliseconds. They grow during their passage through the low pressure region and then collapse as they enter the region of increased pressure. If the bubbles have a relatively large initial gas content, they will collapse and then rebound, as in these high-speed photographs taken by Knapp and Hollander some years ago. These bubbles were formed in the low-pressure region near a body of revolution. Only a small portion of the flow field is shown. These bubbles were formed in the interior of a water sample subjected to an alternating pressure field. If such cavitation bubbles remain spherical throughout their life history, extremely high pressures would be developed upon collapse when the bubble is almost microscopic in size. Estimates indicate the pressure produced near the position of minimum radius is of the order of thousands of atmospheres. However, the bubbles become unstable during their motion and do not maintain a spherical shape. These photographs, taken by A.T. Ellis, show how distortion may proceed. Such deformations tend to reduce the velocity of the bubble wall and consequently the pressures that are developed. If the bubble collapses in an unsymmetrical pressure field, as in this experiment with a bubble at a wall,